Yeah, non-talent show, exactly. Okay, so we were looking at variations in the use of the Boltzmann distribution the past few times, right? And the partition function. So we looked at a three-level system without degeneracy, calculated the partition function. We looked at a three-level system with degeneracy in the upper levels, which is kind of like a rotational situation where the ground state was singly degenerate or non-degenerate, and then the excited states were doubly degenerate. And then we looked at the energies associated with those. And what was interesting, we noticed that the energy was different even though the temperature was the same. And what did I connect that to? It was a physical property of materials that I connected that idea of having different energy at the same temperature. Heat capacity. So different materials have different heat capacities. And so some substance at a given temperature may have more energy in it to donate to a system or to accept in a system. And that's why it makes sense to use different gases in energy applications like heat transfer and so on. Why water or steam is different than helium or argon. Okay, some things are insulating, like argon is between our double pane windows, not helium, because helium transmits heat much faster than argon. And so this idea can be seen even in just simple three-level systems with the Boltzmann distribution. The last lecture I introduced molecular energy levels. So we talked a little bit about the translational energy, which was related to the particle in a box energy levels. Rotational energy, which was B times J plus 1, that was the energy equation for rotation. And then the vibrational energy, which was just the vibrational frequency times V plus a half. Okay, so that was the vibrational energy. And then I commented that the energy equation for rotation and the Boltzmann distribution could be used to determine the temperature of a gas. And so this temperature of a gas coming from the rotational energy levels using the Boltzmann distribution is what we're going to do today. But to do this, well, I'll show you again, and I'll ask your question what we should do to solve for this relationship between the maximum rotational energy level and the temperature. So this probability of the Boltzmann distribution, and it's using J values. Can you see that up there? Okay. Is equal to the degeneracy times that Boltzmann factor. So in rotational energy levels, the degeneracy actually has an equation. It's 2J plus 1. And remember, it's e to the minus energy over kT. And since we're dealing with rotation, we have an energy equation, which is B, the rotational constant, times J plus 1, divided by kT. So when I talk about probability of the Boltzmann distribution, this is the probability of the molecules being in these different rotational levels. Okay. So we can think of it this way. Notice how the degeneracy favors excitation because there's 5 levels up here and only 1 level down here. But then the temperature disfavors excitation, so eventually there's not going to be any molecules populated at the really high levels. If we do spectroscopy on this system, we're going to have transitions that come from J equals 0, J equals 1, J equals 2. And so essentially the probability of this distribution will be revealed in spectroscopy, and we'll get something like this. So a spectrum J values will look something like this. So this increase is 2J plus 1 effect, the degeneracy effect. And the decrease is because of the Boltzmann distribution. And the Boltzmann distribution is dependent upon temperature. So what if temperature goes to 0? Let's just look at that really quickly. So if temperature goes to 0, this fraction explodes, doesn't it? So it's e to the minus huge. Okay? That's a tiny, tiny, tiny thing. Essentially it's 0. Okay? And so the probability of all these excited states goes to 0. Okay? But not the bottom one. The lowest energy state, J equals 0, the top is 0. And so it's e to the 0, so the probability of the ground state stays non-zero. So everything drops to the ground state at absolute 0. So at cold temperatures, this Boltzmann is really steep and only this peak survives. At really high temperatures, it drops off very slowly. Okay? So think about this. If T is huge, this fraction doesn't change very much when I add J's. Okay? So there's really very little difference from J to J to J if temperature is huge. Okay? And so then this drop is very, very slow, and so then there'll be lots of peaks that are populated. Okay? And the maximum J value will move to the right. It'll be a higher peak. And so what we're trying to see is this J max, the maximum of this curve, so this is a curve here, this maximum J value, J max, is temperature dependent. Does everybody see that? If I have a high temperature, J max will be big. If I have a really low temperature, J max will be low or small. Can we solve for the maximum of this curve? Essentially, these peaks are defined by this probability. So what should I do to find the maximum value of this? I could do it numerically, right? I could put it in a spreadsheet and calculate a temperature and see which is the biggest one. Okay, that's really easy. But we've got two choices I've heard: integrate or take the derivative. Which is derivative, yes, take the derivative. Why? Because look at this. This curve goes up here, it goes down there. The derivative is the slope. And so here the slope's positive, there the slope's negative, here the slope is 0. So if we take the derivative of this curve and set it equal to 0, then we can find J max. So let's do that. Yeah, we're just going to take the derivative with respect to J. Everything else we'll treat constant. The rotational constant will be constant. Boltzmann's constant is constant. But temperature will actually, when we solve for J max, I mean, it'll be for a given temperature. So at that temperature, treating that temperature as constant, we'll have J max. So we set the derivative with respect to J of P sub J equal to 0. So that will tell us the max. And this will probably take 3 boards worth of math, as if you don't drop any steps. So I'm not going to skip any steps because it's been a while since some of us have had calculus, and so.
Well, this is not getting pretty.
Yeah, I know. So we got a polynomial up front and an exponential here, and so it's going to be 3 steps. So that's okay. It'll be fun. It's going to take the whole class. Okay. So this is our task for today. All right. So I'm going to have D or DJ, and I'll try to write legibly, even though when I go fast it gets ugly. 2J plus 1. And you may do it faster than I do it, but again, I'm not going to skip any steps. So that's our task. Take the derivative of this with respect to J. I see this here, this is 2J plus 1, so I'm just going to multiply this e to the x stuff inside. I'm going to have 2 pieces. Okay, so I'll have 2 derivatives that I can do. So over here, So that's that first piece. And I'm doing this by hand. I could have showed this on the screen and you would have said, oh yeah. But I want you to go with me. Oh, and this is, yeah, I'll say derivative of both. I have two problems now. Wait till you catch up. Right, I've got this piece here and this piece here. I'll just do them separately. Okay, so let's do one. Okay, so that's essentially the derivative of e to the minus x. So we take the derivative of that stuff inside, it's the chain rule. So d dj minus b j plus 1 over kt times e. Yeah, I know. And so then we're doing the derivative with respect to j. So let's go ahead and do that on this piece here. Okay. So here it makes sense to go ahead and multiply for this j through. So we have b times j squared plus b times j. Okay. So let's simplify this again. Yeah, minus. So now we have, like I said, I'm not going to skip any steps. Squared over kt minus j kt. Everybody with me so far? And so this now is pretty simple. I'm taking the derivative of this first piece and the derivative of the second piece. So we actually get to take the derivative now. We have j squared, and that's our variable. So that's going to be minus 2 times b times j. So we'll finish that out here. So is everybody happy with that? We got it? You're ahead of me, that's good. She's like, I'm already done. And that can be simplified a little bit more. You could pull the b over kt's out. Okay. I'm going to erase all of this and do number 2 next. So I want to make sure everybody's caught up. Okay, now for number 2. Number 2 is the product rule. So the product rule, you know, the derivative of f and g is equal to f prime g plus f g prime. Remember that?
Yes.
When you have, so we have a 2j in front, and then we have an e to the minus stuff that contains j on the right. And so we're going to clean that up. And so this will be the derivative with respect to j of 2j plus 2j times we follow that implementation of the product. And what's nice about this is we did 1 already, and so this piece right here is 1, okay, which we'll insert later. Okay. Okay, so this piece right here is pretty easy. The derivative with respect to j of this 2j is just 2. Okay. So this is equal to 2 minus bj times j plus 1 over kt. And then I have 2j times the result for 1 plus 2j. So that's the result for 2. Everybody okay? Now let's put 1 and 2 together. So that's the 1 piece. Then we have the 2 piece. Oops. So that's everything. That's our final, we did it. I took the derivative of the whole thing. We're going to set that equal to 0, which I think is off the screen. That's a whole lot to set to 0. But as you do with all of this calculus is always a hamburger, right? It's the calculus meat between two pieces of algebra bread. Okay, and so we're done with the derivative, but now let's do the bottom piece of algebra and clean it up. And so what can we do? We can pull this exponential piece out and simplify this polynomial in J. Okay, so we're going to pull this whole mess, this e to the minus b stuff out. 0 is equal to some messy stuff times e to the minus b times j plus 1 over kt. Okay. I'm going to multiply this 2j through right here. Okay, so it'll be minus 4bj squared over kt. Everybody okay with that? And then minus 2bj over kt. And I think that's it. All right. Now let's simplify some terms. We have just one quadratic piece, okay, one j squared piece. We've got a couple of j pieces. So I've got, let's write this one up front, minus 4bj squared over kt minus 4bj over kt, and then plus 2. Did I miss something? Oh, it is one more b. Yeah, thank you. And then this piece minus b over kt plus 2. Yes, with all the board work. Okay, so what can we say about this system?
It's ugly.
Yeah, it looks a little ugly, but we want to know when this goes to 0. Okay, and we really have two pieces that could go to 0. We have the exponential piece that could go to 0, and we have this polynomial piece that could go to 0. This is the derivative, so we've got the equation for the slope of that curve, and we're setting it to 0. So we're trying to find the piece that can go to 0. Can this exponential piece go to 0? It can only go to 0 at infinity j, and that's not really helpful. Yes, we do have this curve going to 0 at infinite j, but infinite j, I mean, it's always going to be infinite j. That's sort of a result that's not helpful. So we could say that really this piece doesn't go to 0 in a region that's useful to us. Does that make sense? It's kind of like when you do factoring and you have x plus 3 and x minus 2 equals 0. The x plus 3 could go to 0, x minus 2 could go to 0. And so you set each individually to 0 and you got your two roots, right? You've got that one root is when the x plus 3 goes to 0, the other root is when the x minus 2 goes to 0, and you have your two roots for a quadratic, okay? In this case, this piece doesn't go to 0, so that's the only piece that can go to 0. And so let's just erase the board and set just this piece to 0 to solve for j. Can we simplify this? I think so.
Yeah, the negative BJ, or no, it's negative BK.
So we can, let me get rid of these parentheses. We don't really need them. Let's just work on this piece right here. Can we simplify this piece? Just forget that 2, okay? We could pull a minus b and j, yeah, so minus b over kt out of there, okay? And we end up with j squared plus 4 plus 1. Huh?
That 40 squared.
Yeah, 4j squared, yeah.
Okay, sorry.
Thank you. It's okay. All right.
That's a square, what's it called?
Yeah, that's an interesting one. Which one is it?
That's 2j plus
2j plus 1 squared. Okay, so this is great. Minus b over kt. Oops, big T. What is it? 2j plus 1 squared plus 2. Is it equal to 0? And notice we have this minus piece and this plus 2 piece. We could bring this over here and set that equal to 2. There's lots of things we could do with this. So let's see, what do we want to do? Let's go ahead and do that. So what we're going to do is we're going to essentially move that equal sign over here between the two. So we have b over kt times 2j plus 1 squared is equal to 2. We could solve for t in this case. So t is equal to b over 2k times 2j plus 1 squared. And so now we've solved for the temperature, and this j is a particular j. Which j is it? It's j max. Right? That's the j value at which that curve is a maximum. So we could even write in j max. So if we find the maximum j value in a spectrum, we know the temperature. We've got to know the rotational constant, which we can look up in the CRC. And we've got to know Boltzmann's constant. We can do that. We just make sure the units are compatible. So we'll do wave numbers in both, and we're set. Let's solve for J max in function of temperature. So if I give you the temperature of the spectrum, which peak would be the maximum? Okay, so I'm going to move all of these pieces to the other side. So J max is equal to 2kt over b. So I move those over. I'm going to take the square root of that, right? So I move this over. I'm going to take the square root. Then I'm going to subtract 1, okay? That 1 is outside the square root. And then I'm going to multiply the whole thing by 1/2 to divide by 2. Did everybody, so check that out mentally, just walk your way through that. And so I can have either a temperature if given a J max, or if given a temperature, I can solve for J max. How are we doing on time? Oh, so perfect. Happy about that. So we have 4 minutes. Now let's look at some experimental spectrum. Okay? So in your in Blackboard, I had this presentation with some rotational spectra. And so here we have the spectrum, it's real vibrational spectrum, but take my spectroscopy course to understand how that works. We get a vibrational transition and a rotational transition happening at the same time. And so what we see on the right and the left is this exact shape. And that peak pattern is governed by this equation, this probability equation. And so one of those values is the J max, and I've labeled the J values. So you can see here, the lower state J values are 1, 2, 3, 4, 5, 6. And this is hydrochloric acid, or HCl, in the gas phase. And you see, here's the maximum of peak 2. And then 3. So 2 is J max in this case. And here it starts at 0 on the R branch side, then 1, then 2. So 2 is J max on both sides. So they kind of confirm each other. All right? So what temperature is this gas? Okay, so J max is 2. So you can put that in. 2 times 2 is 4, plus 1 is 5, squared 25, times 10.59, divided by 2, divided by 0.695 wave numbers per Kelvin. So don't use the 1.38 because that's in joules. So then that gives us a temperature. And the temperature that we get from that for HCl, let's see, where is it? What did you get?
190.5.
One more time?
190.5.
190.5, okay? What if J3 was max? So put in 3 here. You get 6 plus 1 is 7 squared 49 times B divided by K divided by 2.
Yes, 373.
373. So it's between what'd you say, 190?
Yeah.
And 373. So J equals 2 or 3 has a pretty big range. And notice they're not that far apart. I mean, that maximum value is somewhere between those two. Notice that the slope of this temperature, depending upon J max, the slope is B, and B is 10. So if you change the J value, it's like a factor of 10, change in terms of the temperature. So maybe we could find a molecule with a smaller rotational constant, smaller than 10. And sure enough, carbon monoxide. So here's the spectrum of carbon monoxide. Look how many J values we have, because B is 1.9. Yeah, so you're looking on here now. The maximum value is 6. It might be 7. Yeah. You got a different B value.
I got 312.
Yeah, 312. Again, pretty close to 298, which is room temperature. Okay. So this is a carbon monoxide gas, and again, it's in the lab, and so you put in the maximum J value, and you could get the temperature. Or you could say, what value would come from 298? So somebody do that calculation quickly. Put 298 in for this temperature. Use 0.695 for the Boltzmann's constant. That's the wave number value. Times 2 divided by the B up there, 1.593. Okay. Square root, subtract 1, divide by 2. And so 6.8. And so it's telling us that for room temperature, somewhere between 6 and 7 should be the max. Oh no, here's 6 and here's 7. So the max should be sort of between those two values at room temperature. So that's reasonable. It's telling us either 6 or 7 at room temperature ought to be your maximum peaks. Okay. We could even tighten things up a little better and do carbon dioxide. Now, carbon dioxide is really weird in a sense because of the spin parity relationships. There are no even rotational levels. And we can have a discussion about that in my office if you want to know why. But all the even rotational levels are gone because of the symmetry of the wave function. It's amazing because oxygen has a spin of 0 that half the rotational levels disappear. And so in this CO2 spectrum, we start at rotational level 1, and then it goes to 3, 5, 7, 9, 11. And so the max here is, between 9, 10, 11, or 9, 11, 13.
For 13, I got 205.
205 for number 13 for CO2. I typed in 15 and got 270, and I did 17 and got 344. So I want you to think about this example, and I'm going to ask you thinking questions about what your opinion is on how good this is at telling temperatures. Okay? And then I'm going to ask you a thinking question about how might you make this better. There's no perfect answer to that. This is that highest level of cognitive thinking about creating an answer. So I'm telling you, that's going to be one of the exam questions, is how to make this better. What way would you do it? And I would like for you to y'all can discuss the problem. I'd like you to keep your solutions to yourselves.
What do you mean by this?
This using rotational transitions like this to determine the temperature. So is there a better way to treat the data than the way we're doing it? Okay, and I'll leave it at that. Again, I want you to think about this problem. I want you to say, if I had to do this for my job, and I wanted the most accurate temperature measure possible, what would I do? It doesn't mean that you have to do it, but how would you approach the problem? What would you do? This is your job. You've got rotational spectra in the Earth's atmosphere, and I want you to tell me the temperature as confidently as you can. How would you approach that problem? Okay? And I'm giving you a benefit of telling you this problem ahead of time so you have time to think about it. And so when we do our first exam, that's going to be one of the thinking questions. So again, keep your answers somewhat unique. I mean, you don't have to say, oh, they did it that way, but you need to be explained why that solution is a good one. Okay? And even if it's some crazy thing, if you explain it well, you explained it well, right? It's defending your answer. That's what I'm after. Okay. It's not necessarily the right answer because I don't know if there's a right answer. Okay. All right, we need to leave.